Now next topic, that is electrostatics of conductors. So electrostatics of conductors, in that we have to understand certain fundamental things related to conductors. So first thing, inside a conductor electric field is zero. So how we can say inside the conductor electrostatic field is zero? Because inside the conductor there is no motion of electric charges in a particular one direction. If electrostatic field is there, then definitely the electric charges will experience the force, and under the effect of that force it will execute motion in a particular direction, and due to that the current will be constituted. But practically we never observe this thing, so we can say inside a conductor electrostatic field is zero. Second thing, at the surface of charged conductor electrostatic field must be perpendicular to the surface at every point. Now how we can say this electrostatic field is perpendicular to the surface? Because suppose at the surface of the conductor the electric field is not perpendicular to the surface. Suppose it is not perpendicular. Then what happens? If electrostatic field is at some other angle, then you will get two components of electrostatic field. One is perpendicular to the surface, another one is parallel to the surface. And if parallel to the surface electrostatic field is present, then the electric charges will experience the force due to this electric field, and it will constitute the current at the surface. But there is no current on the surface, so we can say when the charged conductor is there, then charges are stationary on that, and we can say that is only possible if the electric field is perpendicular at each and every point on the surface. Now the interior of the conductor can have no excess charge in the static situation. Here, if net charge of the conductor that is equal to zero, then and then only it is possible electrostatic field is zero. So in accordance to that we can say this thing, here there is no excess charge inside the conductor. Now electrostatic potential is constant throughout the volume of the conductor, which is equal to the value of the potential which is at the surface. And if inside the conductor electric field is zero, then we know this thing, electric field E, that is equal to minus dV by dr. So differentiation of electric potential with respect to the displacement, that is equal to zero, means electrostatic potential that is constant one. Now electric field at the surface of a charged conductor, its value. So how we can calculate it? Suppose here we consider a conductor which one is charged 1, and here the surface charge density, that is sigma. Now here consider a pillbox type infinitesimal small Gaussian surface. Partially it is inside the conductor, partially it is outside the conductor. Now at the surface electric field is perpendicular to the surface, we discussed it. Now here for this electric field component in this particular direction, that is zero, it implies that if we think about the surface which one is a cylindrical one, for this pillbox the flux associated with it, that will be equal to 0. or in other words we can say electric field, and here the area vector will be perpendicular to each other. So flux passing through it is 0. Now for this lower surface, it is inside the conductor. Inside the conductor there is no electric field. So flux passing through it, that is also 0. So here flux will pass only through this particular flat surface. Here electric field and the infinitesimal small area vector, both will be parallel to each other. So we can say flux passing through this Gaussian surface E dot delta S, that is as per Gauss's law, sigma q upon epsilon 0, where sigma q, that is the net charge enclosed by the surface. So here net charge that will be enclosed by this surface area which is at this surface. So we can say that is sigma into delta S, because sigma, that is surface charge density, that is charge per unit area. So we can write now E delta S, that is equal to E and delta S both are in the same direction. So E dot delta S, that is E delta S cos theta. Theta is 0, cos 0 1. So directly we can write E delta S, that is net charge enclosed sigma into delta S upon epsilon 0. Delta S cancelled. So at the surface, the electric field, that is E equal to sigma upon epsilon 0 magnitude wise, and in vector form we can write vector E, that is sigma upon epsilon 0 n caret, where n caret, that is the unit vector which is in the direction of electric field, or we can say perpendicular to the surface. Then electrostatic shielding. If we think about a conductor with cavity, if we have a conductor with cavity, then inside the conductor anywhere electric field is 0. Suppose this conductor is placed in external electric field, then negative charges will experience the force in the opposite direction of the field. Positive charges will experience the force in the direction of the field. And under the effect of it, the accumulation of charges will take place at the surface. And due to that, here the electric field will be developed. But this electric field developed will be such that the resultant electric field inside the conductor and inside the cavity, that will be 0. So here this particular fact, in any situation, if the charges are there on the conductor, if conductor is placed in the external field, but inside the cavity the electric field always remains 0. So this fact is known as electrostatic shielding, and this one is a very useful feature. If you want to protect any sensitive circuits, electronic circuits which are sensitive to electric field or change in electric fields, then if those circuits are shielded with the help of this concept, then any type of change in electric field on outside it, no disturbance will be there in the electronic circuit. Clear to all of you? Now example 2.7. A comb run through one's dry hair attracts small beads of paper. Why? What happens if the hair is wet or if it is a rainy day? Remember, a paper does not conduct electricity. Now see here what happens when a comb runs through one's dry hair. At that time, due to friction, the teeth of the comb will be charged, or in broad sense we can say the comb will be charged. So when a piece of paper is placed close to it, then the molecules of paper will be polarized, and due to that it will be attracted by comb. But when the hair is wet or it is a rainy day, at that time the friction reduces. So when you comb the hair at that time, due to absence of friction, comb will not be charged and it will not exert any attractive force on the piece of paper. Clear? Then second question. Ordinary rubber is an insulator, but special rubber tires of aircraft are made slightly conducting. Why is this necessary? When the aircraft lands at that time, due to tremendous high speed, there will be tremendous large friction between the rubber tires and the runway. And due to this friction, large amount of charge will be accumulated. And if these tires are not made conducting one, then what happens? If excess charge is deposited on the tires, then it will be leaked and there are the chances of fire, or we can say accident. But if the tires are slightly conducting one, then due to friction, whatever the charge is deposited on it, it will be earthed with the help of that tire only. And third question. Vehicles carrying inflammable materials usually have metallic ropes touching the ground during motion. Why? The same reason. Because when with high speed the vehicle is moving, at that time, again due to friction, the charges are accumulated on the tank, and if these charges are not earthed, then again there are the chances of fire. Okay? Then D. A bird perches on a bare high power line and nothing happens to the bird. A man standing on the ground touches the same line and gets a fatal shock. Why? Because for the current to pass through the body, there should be the potential difference. If bird perches on a bare high power line, at that time bird is at the same potential. But if man touches the wire and standing on the earth, then due to potential difference, current will be constituted, and if current passes through the body, then it becomes fatal one. Clear to all of you? Now the next topic, that is dielectrics and polarization. Dielectric substance, that is non-conducting substance, and dielectric substances are divided in two categories: non-polar dielectrics and polar dielectrics. In dielectric substance, free movement of charges, that is not possible, just like conductors. Okay? Now, are divided in two parts, or dielectrics are of two types, polar and non-polar. Now, which dielectric substances are known as polar dielectrics and which are known as non-polar dielectrics? If the dielectric molecules possess permanent dipole moment, it implies that in these molecules the centers of positive and negative charges are slightly separated from each other. So it will give you a dipole. So it will possess a permanent dipole moment. So those molecules which possess permanent dipole moments are known as polar dielectric substances, and those molecules which does not possess permanent dipole moments. It implies that in such molecules the centers of positive and negative charges coincide with each other or superposed to each other. So dipole that will not be formed. So this type of molecules which does not possess the permanent dipole moment are known as non-polar dielectric substances. And see here, non-polar dielectric substances are H2, O2, CO2, and polar dielectrics are like HCl, H2O, all these molecules. Clear to all of you? Now, next topic. Conductor and dielectric in external field. See, now if we place any conductor in external field, then inside the conductor there are positive, negative charges. Net charge in the conductor, that is 0. Now when it is placed in the external field, negative charges will experience the force in the opposite direction of the field, and positive charges will experience the force in the direction of the field. So here positive charges will be accumulated on the surface, which one is in the direction of the field, and opposite to it negative charges will be accumulated. And due to these positive and negative charges inside the conductor, the electric field will be developed. But till the net electric field inside this conductor, this external plus internal, that is not equal to 0, the accumulation of charges will continue. And when this external and this internal electric field becomes equal, then net electric field becomes 0. And when net electric field becomes 0, then after the accumulation of charges will be stopped. This type of behavior will be observed for the conductors when are placed in the external field. When dielectrics are placed inside the external electric field, no doubt here also the negative and positive charges will be accumulated at the surface. But here this accumulation will not be such that the net electric field inside the conductor, that inside the dielectric, that becomes 0. It does not become 0. That type of accumulation does not take place here, right? So here if dielectric is placed, no doubt some accumulation of charges will be observed, but due to this accumulation of charges, the electric field developed inside this one, that will not be equal to this external field. So net field inside it will not be 0. And here the maximum electric field that a dielectric medium can withstand, that is called its dielectric strength. And for air it is about 3 into 10⁶ volt per meter. It implies that, see, air, that is the dielectric medium, non-conducting medium, if electric field strength is beyond this one, then what happens? Its dielectric characteristic that will not withstand. Breakdown will take place, its ionization will take place, and now it behave as conducting medium, and through it the flow of charge will start. So the maximum electric field strength a dielectric medium can withstand without breakdown, that is called its dielectric strength. Clear to all of you? Now next topic, polar and non-polar molecules in external field. See, we already discussed this thing. Polar molecules possess permanent dipole moment, and non-polar molecules does not possess permanent dipole moment. But if we think about the non-polar dielectric substance. Then for entire substance, the net dipole moment will be 0 because each molecule have the dipole moment equal to 0. But for polar dielectric substance, each molecule possesses permanent dipole moment. But here, due to thermal excitation and random orientation of all the dipole moments, if we take the vector summation of all the dipole moments, the net dipole moment of the polar substance, that is also equal to 0. But when these substances are placed in the external field, then both the substances will get some net permanent dipole moment. How? See, if external field is 0, then for non-polar molecules, center of positive negative charge is superposed and it does not possess dipole moment. But if it is placed in the external field, then due to the force on positive and negative charge, these centers of positive negative charges will be displaced under the effect of this force of external field. And now each molecule will possess some dipole moment, or we can say for each molecule the dipole moment will be induced. So here some net dipole moment will be obtained. Similarly, if we think about the polar molecules, then each polar molecule have some dipole moment. But due to random orientation of all these, the net dipole moment of the substance, that is 0. But in the external field, again, the positive charges will experience the forces in the direction of the field, negative charges will experience the forces in the opposite direction of the field. So all the dipole moments will try to align themselves in the direction of the field. And due to that, again you will get some net dipole moment. Clear? So if non-polar or polar molecules are placed in the external field, both will have some net dipole moment, or we can say some net dipole moment will be developed in both type of substances here. Right? Now, suppose we think about the case of very low temperature. And in that particular case, if we think all the dipole moments are perfectly aligned with external field, then see, in this particular manner all the dipoles are aligned here. Now here what happens, this positive negative, this positive negative, this positive negative will nullify each other. So in this particular case, here at this particular surface, some net negative charge will be induced. Here we can say this surface charge density, that is minus sigma p. This alignment of all the dipole moments along the electric field, that is called polarization of the molecules or substance. Okay. So when the substance is polarized, here on this side the negative surface charge density due to polarization will be developed, and on other side the positive surface charge density will be developed due to polarization. Clear? Now the dipole moment per unit volume, that is called polarization P. Here dipole moment induced, or we can say some net dipole moment is induced. So the net dipole moment per unit volume, that is called polarization P. And here for linear isotropic, dielectrics, we can write P, that is chi E, where this constant is the characteristic of the dielectric, and that is known as the electric susceptibility of that dielectric substance, or we can say dielectric medium. Clear to all of you? Now the next topic, that is capacitors and capacitance. Now capacitor means what? Capacitor is a system of two conductors separated by insulator, or we can say insulating material. Now one conductor have charge plus Q and another conductor have charge minus Q, and the potential difference between these two conductors, that is V equal to V1 minus V2 between these two. Clear? Now here the charge of the capacitor is said Q. Charge of the capacitor is said Q, and the total charge of the capacitor, that is the summation of these two, so that will comes to 0. Now here the electric field between these two conductors, that directly proportional to the charge Q. So we can understand this thing: if electric field directly proportional to charge Q, then this potential difference also proportional to charge Q. But here Q by V, that remains constant, and this particular ratio Q by V, which remains constant, that is known as capacitance of capacitor, and it is denoted by C. Now here this capacitance of capacitor, that is independent of Q and V. It depends only on the geometric parameters of capacitor. It implies that the shape of the conductors, the size of the conductors, the separation between the conductors, and the medium between the conductors. Okay. Now the unit of capacitance, that is coulomb per volt, and this coulomb per volt, that is known as farad. On behalf of the name of scientist Faraday, it is known as farad. This 1 farad unit, that is tremendous large unit. So in practice we use small units like microfarad, nanofarad, picofarad. Now 1 microfarad, that is 10 raised to minus 6 farad, 1 nanofarad, that is 10 raised to minus 9 farad, 1 picofarad, that is 10 raised to minus 12 farad. Here you have to remember this thing: farad is large unit. So in most of the cases when you deal with any problems, any MCQs, at that time the unit of capacitance that will be given to you, like microfarad, nanofarad, picofarad. So first of all you have to convert it in farad, and then after you can use it. Now circuit symbol for the fixed value of the capacitor. The capacitor connected in the circuit, that is suppose with fixed value, then it is denoted by this symbol. Here two parallel lines, and both the parallel lines are equal in size, and the variable capacitor, it implies that the capacitor which one is connected in the circuit, its capacitance is variable. Symbolically it is represented in the circuit with the symbol of the capacitor with arrow on it. Clear to all of you? Now next topic is the parallel plate capacitor. Here we have to find the capacitance of a parallel plate capacitor. Now in parallel plate capacitor we have to take two plain parallel conducting plates as shown in the figure, and these two plates are with large area and the separation between these two plates, that is equal to, suppose, small d. And here we have to take the medium between two plates, that is vacuum. Now here plate number 1 is possessing charge plus q, and on plate number 2 there is charge minus q. Clear? Now here surface charge density of plate 1, that is plus sigma, and for plate number 2 that is minus sigma. Now first of all here we have to find the electric field in different regions. Now see here, we know this thing, electric field due to charged plane, that we studied in chapter number 1. So that is sigma upon 2 epsilon 0. In chapter number 1 we derived this thing. So for positive charge, the electric field that is going out from the charge, and for negative charge it is from infinity to charge. So here if we think about the electric field of positively charged plate, then its electric field on left hand side, that is starting from the plate up to infinity with value sigma upon 2 epsilon 0. Similarly on right hand side also from plate up to infinity sigma upon 2 epsilon 0. Then for negatively charged plate, the electric field, that is from infinity to plate. So on left hand side from infinity to plate with magnitude everywhere sigma upon 2 epsilon 0. Similarly on right hand side from infinity to plate, that is the direction, with magnitude sigma upon 2 epsilon 0. Now let's think about the net electric field in all these different regions. So see, suppose we think about the electric field in region number 1. So here due to positive plate, the electric field, that is sigma upon 2 epsilon 0. Due to negative plate it is also sigma upon 2 epsilon 0. But see the directions of these two, that is opposite to each other. So net field, that is sigma upon 2 epsilon 0 minus sigma upon 2 epsilon 0, and that is equal to 0. Similarly on right hand side, the field due to positively charged plate, that is sigma upon 2 epsilon 0, right, going to infinity, and due to negatively charged plate from infinity to the plate, magnitude again sigma upon 2 epsilon 0. So here both the fields are equal in magnitude but opposite in direction. So again in this region number 2, the net electric field will be equal to 0. But see, here there is the different case between these two plates. Now see here, due to positive plate, the electric field between two plates, that is sigma upon 2 epsilon 0. Due to negative plate also it is sigma upon 2 epsilon 0. But both the fields are in the same direction. So net field will be sigma upon 2 epsilon 0 plus sigma upon 2 epsilon 0. That is sigma upon epsilon 0. Now sigma, that is surface charge density, area of the plate is A, charge on the capacitor, that is Q. So we can replace sigma, that is Q by A. Now potential difference between these two plates of the capacitor, that is V equal to electric field into the separation between these two plates. So E into D. So substitute the value of E. So E, that is Q upon epsilon 0 A. Clear? Now, as per definition of the capacitance of capacitor, we take capacitance C, that is Q by V. So here if we take Q by V from this equation, then capacitance will be epsilon 0 A by D. So here we can see this thing, capacitance depends on the dimensions of the capacitor. It depends on the area of the plates, the separation between the plates. Clear? Now see here, in previous topic we discussed this thing, the capacitance of capacitor is measured in the unit farad. Farad, that is tremendous large unit. That is tremendous large unit. Now how large is this one? Let's try to understand this thing. Suppose we want to make a capacitor which capacitance equal to 1 farad. So for that we consider the separation between two plates, that is 1 millimeter. So if by keeping the separation between two plates 1 millimeter, if we want to prepare a capacitor having capacitance equal to 1 farad, then what should be the area of the plates? Let's calculate. So here C, that is epsilon 0 A by D, so A, that is CD upon epsilon 0. C 1 farad, D 1 millimeter, so 10 raised to minus 3 meter, epsilon 0 8.85 into 10 raised to minus 12. If we solve this one, then answer will be nearly equal to 10 raised to 8 meter square. So we can write this one as 10 raised to 4 meter into 10 raised to 4 meter. Suppose we think about the square plate. Okay. So length and breadth of the plate, that will be 10 raised to 4 meter to 10 raised to 4 meter. Means 10 kilometer by 10 kilometer. Means if we take two conducting plates with length and breadth equal to 10 kilometer, and then after if these two plates are separated by 1 millimeter, then we will get a capacitor of capacitance 1 farad. Now imagine a conducting plate having dimension 10 kilometer by 10 kilometer. Then the capacity of the capacitor that can be obtained 1 farad. So this farad, that is tremendous large unit. Okay, so it is too big unit. Clear to all of you? Dear students, we studied about the dielectric substances and polarization of dielectric substances. Scientists observe this thing: when dielectric substance is introduced between two plates of the capacitor, its capacitance can be increased considerably. So let's understand this thing. So effect of dielectric on capacitance. Suppose first we think about a parallel plate capacitor with no medium between two plates. It implies that there is vacuum between these two particular plates. Suppose charge of the capacitor is Q, and here area of the plates, that is A, the separation between two plates, that is D. Now when there is no medium between these two plates, it implies that when there is vacuum between these two plates, at that time the electric field between these two plates, that is sigma upon epsilon 0. We derived these equations. Then potential difference between these two plates, that is V0, that is E0 into D. And the capacitance of the capacitor, that is epsilon 0 A by D. Okay. Now, if the dielectric substance is introduced between these two plates of the capacitor, then we know this thing due to polarization of the dielectric in the presence of external field. Here which field is present? So electric field of this capacitor means electric field between two plates of the capacitor, that is present. And now in that particular electric field, this dielectric substance is introduced. So here what happens? Resultantly, at the surface of the dielectric substance which is close to the positive plate of the capacitor, the negative charge will be induced. And here the surface of the dielectric substance which is close to the negative plate, the positive charge that will be induced. So inside the dielectric substance, due to its polarization, here suppose the surface charge densities are plus minus sigma p, and due to that the electric field in the opposite direction of the external field will be developed, and that is EP equal to sigma p upon epsilon 0 as shown in the figure. Clear to all of you? Now see, here the electric field resultant one, that is E0 minus EP. E0 that is sigma upon epsilon 0, EP that is sigma p upon epsilon 0. So here we can say the resultant electric field between these two plates of the capacitor, that is E equal to sigma minus sigma p upon epsilon 0. Now easily you can understand this thing. This sigma p directly proportional to sigma. So we can say this sigma minus sigma p, that also proportional to sigma. Here we can say the potential difference V, that is E into D. So that is sigma minus sigma p upon epsilon 0 into D. Now if sigma p proportional to sigma, then we can say sigma minus sigma p also proportional to sigma. So sigma minus sigma p proportional to sigma, so that we can write sigma minus sigma p, that is sigma by k, where k, that is the proportionality constant here, that is the characteristic of dielectric substance, and its value that is always greater than 1. So here sigma minus sigma p, if we replace by sigma upon k here, then we can write E, that is equal to sigma upon k epsilon 0, and you can write V, that is equal to sigma upon epsilon 0 k into D. Now see, when V, that is sigma d upon epsilon 0 k, here we replace sigma, that is the surface charge density, that is Q by A. So we can write QD upon A epsilon 0 k. Now the capacitance of the capacitor, that is the ratio of charge to potential difference. Here on the capacitor, charge is Q. When dielectric substance is introduced between two plates of the capacitor, there will be no change in the charge which is deposited on the plates of the capacitor. So we can write here, now new capacitance of the capacitor when dielectric substance is introduced, that is C equal to Q by V. So we can write C, that is Q by V, that is epsilon 0 k A by D. But epsilon 0 A by D, that is original capacitance of the capacitor when the dielectric substance was not introduced. So we can write C, that is equal to KC0. Here this K, that is known as the dielectric constant of that particular dielectric medium or dielectric substance. So we can say this thing, when the dielectric substance having dielectric constant K is introduced between two plates of the capacitor, then capacitance of the capacitor that is increased by K times. Now epsilon that is equal to epsilon 0 K. So here we can write this epsilon 0 K, that is epsilon, which is known as the permittivity of that particular medium. Permittivity of that particular medium. So here we can write K, that is epsilon upon epsilon 0 also, and epsilon upon epsilon 0, that is known as the dielectric constant of the substance. It is also known as relative permittivity of that particular dielectric substance. Clear to all of you? Now example 2.8. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor, but has a thickness 3 by 4D, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? Now see here, in theory we studied this thing when the dielectric substance is introduced between two plates of the capacitor. At that time the capacitance is increased by K times. But in that particular case we consider the entire space between two plates is filled with dielectric substance. Here the thickness of the dielectric, that is 3/4 D, and separation between two plates, that is D. So we can say in some part of this particular space between two plates of the capacitor, the dielectric substance is introduced. So first understand the situation. Say here, this separation is D, and the dielectric substance introduced here, that is with thickness 3D by 4. So when dielectric substance is not there at that time, the electric field between two plates of the capacitor, means when there is the vacuum, electric field is E0. So now the portion in which there is no dielectric substance, there the electric field will remain same one, E0. In the region where the dielectric substance is there, inside it the resultant field, that is 1 upon K times, so E equal to E0 by K. Suppose here in this portion with thickness D by 4, where there is the vacuum, the potential difference is V1, and inside the dielectric slab there is the potential difference equal to V2. This portion is D by 4, this portion is 3D by 4. Clear? Now see here, we can write here V0, that is equal to E0 into D. So here the resultant potential difference between these two plates of the capacitor, that we can write V1 plus V2. Now here V1, as per this equation we can write electric field into this particular separation. Here also potential difference, that is electric field into this particular separation. Now V0, that is equal to E0 is sigma upon epsilon 0 into the sigma, that is Q0 by A. So here capacitance C0, that is epsilon 0 A by D, and that is Q0 upon V0. All these things we already discussed, that is just mentioned here. Okay. Now when the dielectric slab is inserted, the potential difference V, that is V1 plus V2. So we can write V, that is V1, electric field in this region, that is E0, into this particular distance, that is D by 4, so that is V1. For this V2, that is electric field E0 by K, this particular distance, that is 3D by 4. So now we can take E0 D by 4 common, so we can write 1 plus 3 by K here. Clear up to this one? So here we can write E0 into D, that is V0. So V0 by 4, take here K LCM, so K plus 3 by K. Now, C that is Q0 by V. So, here we can write C that is equal to Q0 by V. V that is V0 by 4 into K plus 3 by K. So, we can write here V that is equal to this one. So, directly if we substitute, then 4K upon K plus 3 into V0. So, here Q0 upon V0, that is our original capacitance. So, we can write C that is equal to 4K upon K plus 3 into C0. It implies that if the dielectric slab having dielectric constant K and thickness 3 by 4D is introduced between two plates of the capacitor where the separation is D, the capacitance that becomes 4K upon K plus 3 times the original capacitance. Clear? Now next topic, that is combination of capacitors. Here capacitors can be connected in two ways in the circuit. One that is series combination and another one that is parallel combination. So first, capacitors in series. When capacitors are connected with the battery as shown in this figure, then this particular connection of the capacitors, that is known as a series connection or series combination. Here, if this particular battery induce plus Q charge on the plate of the capacitor, then at the opposite plate minus Q charge will be induced. This minus Q charge will induce plus Q charge on the first plate of this other capacitor. It will induce minus Q charge on the other capacitor. So here, very important thing in this combination, that is this one. In series combination of the capacitors, the charge on each capacitor will be same one. Now here, suppose first capacitor that is with capacitance equal to C1 and second one that is with capacitance C2. And charge on both the capacitor that is same Q. It implies that potential difference across each capacitor will be different one. Suppose here the potential difference is V1 and here the potential difference is V2. So this resultant potential difference of the circuit or resultant potential drop across the combination. So that potential drop V that we can consider between these two particular points. Between these 2 points, there is the series combination of capacitors. So here, the resultant potential drop V that we can consider as V1 plus V2. Clear? Now, C that is Q by V. So V that is Q by C. So V1 that we can write Q by C1 and V2 that is equal to Q by C2. If we take Q common here and then take it on left hand side, so V by Q equal to 1 upon C1 plus 1 upon C2. Suppose here we consider the effective capacitance of this capacitor, that is C. Then it will be also with charge Q. So if we consider the effective capacitance of this capacitor with charge Q and potential difference that will remain the same one, then we can write C that is equal to Q by V. And now here we can write 1 upon C that is V by Q. So if we substitute this particular value V by Q, that is 1 upon C, then we can write 1 upon C equal to 1 upon C1 plus 1 upon C2. Okay. Now, here for n capacitors arranged in series, we can write the generalized equation, that is V equal to V1 plus V2 plus V3 up to Vn, and that is Q by C1 plus Q by C2 up to Q by Cn. As per this one, then we can write 1 upon C, that is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 up to 1 upon Cn. Clear? Now, from this particular equation, you can understand this thing. In series combination of capacitors, the resultant capacitance, that will be smaller than the smallest one connected in this combination. Now, if all the capacitors are with same value, then here we can write 1 upon C, 1 upon C, 1 upon C n times. So that is n by C. So if we take reciprocal of this one, then C effective, that is C by n, where n, that is the number of capacitors in the given combination. Clear to all of you? Now, parallel combination of capacitors. So capacitors in parallel. Suppose the capacitors are connected with the supply as shown in this figure in such a way that 1 plate of each capacitor that is connected with positive terminal of the battery and other plate of each capacitor that is connected with negative terminal. Then this type of connection of the capacitors, that is known as parallel combination. So here in parallel combination, across these common points here, the potential difference will be same one. Now capacitance of each capacitor, that is different one. Suppose for this one the capacitance is C1, for second one C2. Now potential difference across each one is same one. Obviously C, that is Q by V, V that is same one, C that is different one. So charge deposited on each capacitor will be different one. Clear? So here we can write the net charge Q supplied by the supply or the battery to this entire combination, that we can write Q equal to Q1 plus Q2, where Q1, now C that is Q by V, so Q that is CV, so Q1 that is C1V, Q2 that is C2V. So total electric charge, that is Q equal to Q1 plus Q2. Clear? Now substitute these values of Q1 and Q2. So we can write Q that is C1V plus C2V. Take V common, take it on left hand side. So we can write now Q by V, that is C1 plus C2. Now suppose here the effective capacitance for this parallel combination is C. Then effective capacitance means same supply will give you the same amount of charge if this combination is replaced by only one capacitor. Then we can write C, that is Q by V, but here we can see Q by V, that is C1 plus C2. It implies that suppose we have n capacitors connected in the parallel combination, then the effective capacitance, that is C equal to C1 plus C2 plus C3 up to Cn. So from this equation you can say this thing: in parallel combination of capacitors, the effective capacitance, that will be greater than the largest one connected in this particular combination. Suppose here we consider each capacitor that is with same value. Then we can write C plus C plus C plus C up to n times. So we can write the effective capacitance, that will be N into C, where N that is the number of capacitors in the given parallel combination. Clear to all of you? Now example 2.9. A network of 4 10 microfarad capacitors is connected to a 500 volt supply as shown in the figure. Determine A. the equivalent capacitance of the network, and B. the charge on each capacitor. Not the charge on a capacitor is the charge on the plate with higher potential equal and opposite to the charge on the plate with lower potential. Now in this particular example, first of all we have to find the equivalent capacitance of the network. This one is the network given to you. Now see here the supply voltage that is across A and D. Here 500 volt supply is given to you. Now see in this upper branch here capacitor C1, C2 and C3 are in series in this branch A, B, C, D. Okay. So here for these three capacitors, the equivalent capacitance will be as per equation 1 upon C equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. But here all the capacitors are with same value. So we can say the effective capacitance that is C by 3. So here the effective capacitance we can take C dash, that is 1 upon C dash equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. But all the capacitors are with same value 10 microfarad. So we can say C dash that is equal to 10 by 3 microfarad. Now if these three capacitors are replaced by only one capacitor having capacitance equal to C dash, then we can say, see here, suppose these three are replaced by only one capacitor here with capacitance that is C dash. Now these three are removed here. Okay. So we can understand this thing. This C dash and this C4 are parallel to each other. So if we take C dash and C4 parallel to each other, then resultant that is C dash plus C4. So resultant capacitance of this particular network between A and B, that will be C dash plus C4. So we can write C that is C dash plus C4, C dash that is 10 by 3 that we calculated, C4 that is again 10. So 10 by 3 plus 10 microfarad that is 13.3 microfarad. Now see here question number B. In that we have to calculate charge on each capacitor. Now we know this thing in series combination. See here across AD in series combination, charge on each capacitor that is same one. So here sorry, suppose we consider charge on each capacitor that is Q. So here charge is Q, here also Q, here also Q. So potential difference across each capacitor, that will be different one. Suppose here V1, here V2 and here V3. So we can say this thing V1 plus V2 plus V3, that is across A to D, and across AD the potential difference applied that is 500 volt. and the same potential difference is across C4. So here if we consider charge on fourth one, that is Q4, then across it the potential difference is 500 volt. Now we can use the equation C, that is Q by V, or we can say V, that is equal to Q by C. Now using this concept, let's calculate charge on each capacitor. See, now charge on capacitors C1, C2, C3 which are in series, we considered charge on each one, that is Q, and charge on C4, that we consider here suppose Q dash. So we can write the potential difference across AD, that is V1 equal to Q by C1 plus V2 equal to Q by C2 plus V3 equal to Q by C3, that is equal to 500 volt. All these three are with value 10, 10, 10 microfarad. So here we can write Q, that is equal to 1 by C1 plus 1 by C2 plus 1 by C3 into 500. So resultant of these three that we already calculated, 10 by 3 into 10 raised to minus 6, because that is microfarad. So into 10 raised to minus 6 into 500. So it comes to 1.7 into 10 raised to minus 3 coulomb. So charge on each capacitor C1, C2 and C3, that is 1.7 into 10 raised to minus 3 coulomb. Now potential difference across C4, that is also 500 volt, and suppose charge on it, that is Q dash. So we can write Q dash by C4, that is 500. So Q dash, that is C4 into 500. C4, that is with value 10 microfarad. So we can substitute here 10 into 10 raised to minus 6 into 500. So we will get the value 5 into 10 raised to minus 3 coulomb. So in this way, we can calculate charge on each capacitor given in the network. Clear to all of you? Now example 2.10. A. A 900 picofarad capacitor is charged by 100 volt battery. Figure A. How much electrostatic energy is stored by the capacitor? B. The capacitor is disconnected from the battery and connected to another 900 picofarad capacitor. Figure B. What is the electrostatic energy stored by the system? Now here, see, value of the capacitor that is given to you, capacitance is 900 picofarad and it is connected with 100 volt battery. So here we can calculate the energy stored in the capacitor by equations which we derived in the previous theory. U, that is half CV square, or we can calculate that is equal to Q square by 2C, or you can calculate by the equation half QV. Say here C and V directly given to you, so you can calculate by this equation also. But suppose you calculate first charge. So charge on the capacitor Q equal to CV. Then C into V. So charge on this capacitor, that is 9 into 10 raised to minus 8 coulomb. Here we calculate now the energy stored in the capacitor by the equation U equal to half QV. So half value of Q, this one, into V. So you will get the answer 4.5 into 10 raised to minus 6 joule. Right? Okay. Here you can calculate by substituting value of C and V here also. You will get the same answer. Right? But first we calculated Q here because it is useful to calculate the second part of this example. How? See, Now the capacitor is disconnected from the battery. So when this capacitor is disconnected from the battery, at that time there is charge Q on it. And now it is connected with another same type of capacitor. So when two capacitors are of same value, then one is not charged one, another one is charged one. So distribution of charge will take place here, and charge will be distributed exactly half. So when this particular capacitor is disconnected from the battery on which charge is Q, if it is connected with the similar capacitor as shown in figure B, then charge on each one will be now Q by 2, Q by 2. So see here, first we calculate energy stored in each capacitor. So here, in steady situation, the charge on each capacitor, that will be Q by 2. So energy stored in each capacitor, suppose in capacitor 1, U1, for capacitor 2, U2. Then U1, that is equal to Q square by 2C as per that equation. Q, that is Q by 2, charge on that capacitor is Q by 2. So Q by 2 whole square upon 2C. So we can write that is Q square by 2C into 1 by 4. But Q square by 2C, that is U. So we can say that is U by 4. Now for second capacitor also the energy stored, that will be the same. So the total energy stored in this particular system. So for capacitor 1, that is U1, for capacitor 2, that is U2. So total energy stored, that is U1 plus U2. So we can write here energy stored by the system of capacitors U dash equal to U1 plus U2. But U1, that is U by 4. U2, that is also U by 4. So U by 4 plus U by 4, that is equal to U by 2. And U that we calculated here. So substitute this value of U in this equation. So you will get 4.5 into 10 raised to minus 6 by 2. So energy stored in the system of these two capacitors, that is 2.25 into 10 raised to minus 6 joule. Now the chapter 2 is completed. So next we will discuss the exercise part of this chapter. Clear?